All right, so now we need to talk about generic attacks in order to talk about non-generic attacks, right? So let's start with the first one, the most obvious and famous one, exhaustive key search attack. Of course, in this one, we are searching keys, but in different scenarios, if you are searching for password, we will call it that exhaustive password search. So we say it's exhaustive search, or it is also called brute force attacks, okay? So if an attacker captures one plaintext and the corresponding ciphertext, they can encrypt the plaintext with every possible key and check if the correct ciphertext is observed, right? Also, you can do the other way around. You can decrypt the ciphertext with every possible key and check if it matches with the correct plaintext. Actually, it is enough to capture only the ciphertext, only one ciphertext block, because the attacker can decrypt with every possible secret key and check if the obtained plaintext is something intelligible. Okay? So this is why I will call this as a ciphertext only attack. Attack type, total break, because we capture the secret key. Data type, ciphertext only attack. Time complexity, 2 to the k encryptions in the worst case scenario. If you are unlucky, this will be in your last trial, which will take at most 2 to the k encryptions. Of course, if you are doing from ciphertext to plaintext side, you can also write 2 to the k decryptions, but most of the time, both of the operations are, almost identical in terms of operations. So here we can say simply as encryptions. Good thing is I don't need to store anything in the memory, right? So you can say none or negligible. It is very simple. Data, either one known plaintext or one ciphertext, but I want to say it's a ciphertext only attack. So only one ciphertext block is enough for you to break the system. So as you can see, with negligible memory, negligible data, but huge amounts of time, I can break the system. But something on the opposite of can also happen. So this I will call table attack, sometimes referred to as dictionary attack. In this scenario, you capture or somehow pre-compute every plaintext and corresponding ciphertext, but you don't know the secret key, okay? So listen to communication for a very long time. So assume that the block size is really small. So you observe every possible plaintext and corresponding ciphertext somehow, but you don't know the secret key. So this actually, with this way, you can store them in a sorted table. So you can either sort them in the plaintext or on the ciphertext side. So your table will be a list of plaintext and corresponding ciphertext, but in a sorted manner. So attack type is global deduction now, because whenever I see a plaintext, I know what the corresponding ciphertext is, but I don't know the secret key. And whenever I obtain a ciphertext block, I can check which plaintext block it corresponds to. So this is an example for a global deduction. Data type, known plaintext, but I actually observe every possible text. So saying that it is known or chosen makes no sense here. I actually capture the whole code book. Okay. Time, negligible, because if I sort it, I can simply find it in a binary search way, so I can easily find the corresponding value. Memory, I need to store 2 to the b blocks in the memory, right? Data, I need to capture 2 to the b. Here, b is the block size, of course, in terms of bits. So I need to capture every possible plaintext, which is 2 to the b. So saying that it is non-plaintext, it actually makes no sense. I need the whole code, okay? So now, this makes something obvious, right? In the previous slide, I had the exhaustive key search attack, which requires trial of every possible keys with negligible memory and data. In this attack, I need negligible data because I'm simply making a table lookup here, but I need huge amounts of memory and huge amounts of data. So question is, can I meet in the middle of these two techniques, right? Time memory trade-off attacks actually does this, but I mean, it is not better than exhaustive search attack, because as a pre-computation, I need to perform this many operations anyway. Okay, so let me explain it. The classical version was introduced by Hellman in 1980, so it's a very old attack, but there are many improvements, improved time memory trade-off attacks, rainbow tables, many variations, but basic idea is simple. Idea is as follows. Even if we have enough computational power to perform exhaustive search for a cipher with small key size, we have to perform 2 to the k encryptions every time to capture the key. So think about A51 stream cipher. The secret key is 64 bits, and I have enough computational power to perform 2 to the 64 operations. It takes months, but I can do it. But question is, if I want to listen to a GSM communication, I have to record it, and I have to perform this exhaustive search attack for months to listen to it. But for every single communication, I have to perform this attack. So question is, can I perform this attack once, then store some of the results so that in the following attacks, I can do it in real time with negligible time or memory and data? Okay. The answer is yes, and this is the time memory trade-off attack. So, but don't forget that I have to do operations more than exhaustive search as a pre-computation. So, idea is to perform exhaustive search in a clever way and store only a small part of the resulting tables. Okay. For example, if you can buy 4 terabytes of hard drive on the market, which you can choose your table size as 4 terabytes. Or if you have 8 terabyte hard drive, then you can increase the size of the table because you have the storage. So this will be your memory complexity at the end. So this is the pre-computation part. So you perform the exhaustive search, but store some values in a huge table. When performing the following attacks in real time, when you capture the ciphertext, the attacker performs less than 2 to the k operations to obtain a value that is already in the tables. Okay? So this is a very nice idea. I will show in the future how to apply it for A51 so that it will be more clear. I will give the main idea, this classical idea, but of course you can then improve it with the to increase the success ratio. You can apply some different techniques. But we will come back to this idea in the future when I talk about A51. Yes, 2 more slides. One of them is the setting. I need to talk about this. Generally, we always assume that we are in the single key setting, which means that I'm trying to break a system. Some people using a block cipher with a secret key, they are communicating. I'm capturing some plain text and ciphertext, and my aim is to obtain this secret key, right? So this scenario is referred to as single key setting. So most attack scenarios consider that only one key is used during the whole communication, and the attacker tries to capture this key. But in real life, generally we don't do this, especially if the block size is small. For instance, in IoT devices, we use lightweight algorithms and the block size is small. So we encourage people to update the key from time to time, because if you use the same key for a very long time, this means that you leaked almost every possible ciphertext, right? So for this reason, we suggest them to update the key. And updating the key on IoT devices sometimes is hard, right? Because there are many devices that scattered around on the field with sensors and so on. So you can apply some basic techniques saying that, okay, initially we agreed on the key, we used it for a very long time, let's increment it by 1. So it is a simple idea, right? But now I don't know the first key, I don't know now the second key, but I know that the second key is just 1 more than the first one. So I know the difference, right? I know the relation. So this is called related key setting. So if you know this relation, by the way, sometimes you can break the system and capture both of those keys. That is the idea. And so you have more power here. So for instance, if there are some ciphers where you can only break 10 rounds when in the single key setting, but break 14 rounds in the related key setting. But of course, that relation will be something you choose, So it is a little bit unrealistic, but it also shows the security of the cipher. So let's look at the related key. Using the same key for a long time can cause information leakage, and the secret key should be changed from time to time. If the used keys have some relations, then the attacker can exploit these relations to capture some or all of the used keys. So this is important because when I said that let's increment it by 1, it was the simplest idea, but we don't use it because I know that there are related key attacks. But people who have no idea about related key cryptanalysis, incrementing by 1 is just a simple solution, and people do it on the field. Okay. Yes, finally, I will talk about side channel analysis, and maybe this might be the last time I do it because in lightweight crypto course we talk about it, but it is important, but this course is not about it. So, side channel analysis is based on information gained from the physical implementation of a crypto system. Attacker requires most of the time as physical access to the device, because sometimes if you're, for instance, performing a catch attack, you don't need to have a physical access sometimes. So, but here, important thing is that we are attacking the physical implementation, not the algorithm itself. For example, differential power analysis measures the power consumption of a device during encryption. Information leaks depending on the power used. For instance, XOR operation requires small amount of power, but an SBox operation requires a lot more. So if the operations are, with the run key XOR operation results depend on run key bits. And if your implementation is not that power sensitive, then we can see actually what is happening and capture some key bits. Okay, just looking at how much power it consumes. So if I have a physical access, I can, measure how much power it consumes. So these attacks generally focus on small devices. You cannot, just look at the CPU of a modern computer because you wouldn't be getting this kind of information just by looking at the power usage. But there are many different versions of side channel attacks. You can even perform attack on the acoustics. The amount of noise the device is, making might allow you to understand what kind of operation it does, right? So these attacks do not break the cipher itself, but it is its implementation. This is important because when people think that AES is secure, they think that it's secure everywhere. But most of the time, the implementation might have this kind of problem. So this is why we actually have an area called lightweight cryptography, where we are trying to design a cipher that is lighter than AES, but also provides side channel security. Because I can make AES and I can change the implementation of AES in a device so that, the power consumption might be almost constant, but the performance will be really small in that scenario, and maybe I will need more area to implement it. So it is a very hard problem. So it is an active research area, but it is, there are no proofs that you can say that, okay, this implementation is, you cannot break it with side channel analysis. You cannot say that most of the time, okay? Because this power analysis or other side channel attack, you can come up with many different versions, and it is very hard to provide. You cannot say that you have provable security against side channel attacks. That is the main thing I'm trying to say.